In this mini lecture, I'm going to look a little bit more at simplifying radicals. And so the first thing we need to talk about are when I have radicals that are involving variables. So some stuff just to keep in mind. Like I say here, we know 4 squared is 16, so that the square root of 16 is the square root of 4 squared, which is just 4, right? The square root of 16 is 4 because 4 times 4 is 16. In the same way, 2 to the 5th is 32. So the 5th root of 32, remember that index of 5 means I need something that I multiply 5 times to get 32. Of course, the way we set this up, we know it's 2. 2 times 2 times 2 times 2 times 2 is 32. And these 5th power and the 5th root, they sort of cancel out and I just get 2. It's probably not surprising then that, like I say here, this happens with variables. If I have the square root of x squared, remember if I don't have an index written, there's really a little 2 there, right? Can I write a little 2? There's really a little 2 there. And what we have here then, the 5th root of x to the 5th is x. So in general, the nth root of x to the n would just be x. The nth root and the nth power sort of cancel out. Now, I've got a note here. This is sort of a technical detail that's not going to be important for this class, but you probably want to be aware of this if you're going to take more math in the future. This statement, the nth root of x to the n equals x, that's always true for odd values of n. So if I'm doing cube roots or 5th roots or 7th roots, this works. But with even values of n, it's more complicated. Consider just a simple square root. If I have negative 4 squared, you would say, oh, well, the square root of something squared should cancel out. That's going to be negative 4. But no, negative 4 squared is 16. Negative 4 times negative 4 is positive 16. And when I use this square root symbol, we always mean the principal square root, which is the positive square root. So that would be 4 and not negative 4. So this negative 4 on the inside gets changed into a positive 4 when I square it and take the square root. So for even values of n, I should really say this then. The nth root of x to the n is not just x, it's the absolute value of x. That forces us to take the positive root instead of the negative root. And so, like I say here, although this is technically true, the directions for many of these problems will specify that you are to assume that all variables represent non-negative numbers. So then this x, we're assuming it's not negative, so then I don't need the absolute value bars. And this is going to be the case for all the problems in this class. But you need to be aware of that possibly in the future. Here's some examples then that go along with this. X to the 6th is really the same thing as x to the 3rd squared. Remember, a power of a power, I would multiply those exponents. 2 times 3 is 6. So the square root of x to the 6th, instead of x to the 6th, I can write this x cubed squared, right? And that's what's here. But what I've got then is I've got a square root of something squared. Those essentially cancel out and I just get x cubed. That happens in all of these examples here. X to the 14th, if I want the square root of x to the 14th, I can think, well, can a 2 go in there? Well, yeah, 7 times 2 is 14, and then the square root and the square cancels out, and I'm left with just 7. Same thing with x to the 20th then. Does 2 go into 20? Yes, 10 times 2 is 20. The square root and the squared cancel out, so I just get x to the 10th. And what I'm noticing here essentially in these examples, we're dividing the exponent by 2, right? 6 divided by 2 is 3. 14 divided by 2 is 7. 20 divided by 2 is 10, right? 6 divided by 2 is 3. 14 divided by 2 is 7. 20 divided by 2 is 10. This works for other powers as well. If I'm looking at cube roots here, the cube root of x to the 12th or x to the 21st or x to the 60th. Well, 12, 21, and 60, those are all multiples of 3. Right? 12 is 3 times 4, 21 is 3 times 7, 60 is 3 times 20. And so instead of these cube roots, I can sort of think of it that way. and then the cube root and something cubed, those essentially cancel out. And so I just get x to the 4th, x to the 7th, and x to the 20th. But what was my original exponent? I had the cube root of x to the 12th. I really have 12 divided by 3 is 4. 21 divided by 3 is 7. 60 divided by 3 is 20. So in these cases, we're going to divide the exponent by 3 because I had cube roots. And this very last example here, then, I'm going to do a 5th root. It's not a big surprise. We end up dividing the exponent by 5. And so, in general, to find the nth root of x to the m, we take whatever that power is on the inside and we try to divide by the index n. So let's look at some examples. So, simplify the radical. Assume all variables represent positive numbers. That's that key that means I don't have to worry about that weird absolute value stuff. All right, so on this first problem, the square root of x to the 40th, if it helps, we can remember that that's really a little index of 2 that's up there. And so what I'm going to have to do is I'm going to have to divide the exponent by 2. And so when I look at that here, 40 divided by 2 is 20. That's really messy. So my answer would be y to the 20th power. Here, I notice my index is 3. So I'm going to divide my exponent by 3. The 27 is different though, right? This 27 isn't a variable, that's a number. So what I have to think there for the 27, I have to think what to the 3rd power is 27. And of course that would be 3 then. 3 times 3 times 3 is 27. And so what I would get, the cube root of 27 is 3. The cube root of x to the 12th, I take 12 divided by 3, and I get 4. In this problem here, there's not an index. If there's not an index, that really means I've got an index of 2. So I'm going to divide any exponents by 2. But for the 121, I have to think what to the 2nd power is 121, and of course 11 times 11 is 121. So the square root of 121 is 11, and then these exponents I'm going to divide by 2. So for the a, I have to take the 24 and divide by 2. 24 divided by 2 is 12. For the b, I'm going to have to look at the 30 and divide by 12. 30 divided by 12 is 15. Okay, and my final example like this, I've got this 5th root of negative 32 x to the 10th y to the 35th. So we do know again it's a 5th root, so that means I'm going to divide in the exponents by 5. But this negative 32, I have to think what to the 5th power is negative 32, and of course that's negative 2. Right? Negative 2 times negative 2 is positive 4, times another negative 2 is negative 8, positive 16, negative 32. And so my answer, the cube root of negative 32 is negative 2, and then I'm going to have to divide these exponents by 5. So 10 divided by 5 is 2, 35 divided by 5 is 7. All right, so that's how I deal with radicals that have variables inside. Notice there's something a little fake about these problems, fake news here. these problems, I could evenly divide the exponent. So I had the fifth root of x to the 10th. If it were the fifth root of x to the 9th, obviously I'd have some trouble. We're going to see how we deal with that next here. We'll have some examples on the next page where we can deal with that. What we end up doing, I still use number 1 here, it should have been number 2. Simplifying radicals using the product rule. So there's something called a product rule for radicals. Where it comes from is the fact that this nth root, remember, we can just rewrite as a rational exponent. The denominator is the root that we would have. The numerator is the power. It's just x to the first power. So if I have the nth root of ab, that's the same thing as the 1 over n power. But if I have a product to a power, I can apply that power to both parts, so I really just get these two nth roots. So if I start with the nth root of a times b, that's the same thing as just the nth root of a times the nth root of b. So I can split up a radical if I'm multiplying. This works if you're multiplying or dividing. It doesn't work if you're adding or subtracting, right? Square root of 4 plus 9 is not equal to the square root of 4 plus the square root of 9, right? Because that would be the square root of 13. That's not equal to 2 plus 3. But the square root of 4 times 9 is equal to the square root of 4 times the square root of 9. Because that would be the square root of 36 is 2 times 3, and 6 is equal to 6. So it works if we're multiplying. It also works if we're dividing. But it doesn't work if we're adding or subtracting. How this can help us then, we can simplify radicals like this. I have the square root of 20. I don't know a number that's squared is equal to 20, right? I'd want to think what squared equals 20. And I don't know what that is. But I can say instead of 20, I can think of it as 4 times 5. So I would get the square root of 4 times the square root of 5. But then the square root of 4 is just 2. Right? The square root of 4 is just 2. Same thing then in this example, if I have the cube root of 24, that would say what to the third power is 24? I don't know. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27, a little bit too big. But I can rewrite 24 as 8 times 3. So I would get the cube root of 8 times the cube root of 3, and then the cube root of 8 is just 2. And so that carries over like that. Realize that if you're going to use this kind of property, it matters how you split up the number. If I looked at the square root of 20 and I said, okay, that's going to be the square root of 2 times 10, that's certainly true. And I can write square root of 2 times square root of 10, but I don't know what the square root of 2 or the square root of 10 would be equal to. So that doesn't help me. The only thing that helps me here is thinking of 20 as 4 times 5. I have to split it up by multiplying, not by adding. I can't say 20 is 16 plus 4. Although that's true, it doesn't help me with this square root. What we say in general then, a radical with index n is simplified if the quantity on the inside has no factors that are perfect powers of n. Now, what do I mean by that? A square root is simplified if the inside cannot be divided evenly by any perfect square. And a cube root is simplified if the inside cannot be divided evenly by any perfect cube. So here for the square root of 20, I would say, is there a perfect square that goes into 20? Well, yeah, 4. So I have to divide by that 4. I have to get rid of that. Is there a perfect cube that goes into 24? Well, yes, 8. So I split it up in that way. So recognizing perfect squares, perfect cubes, that kind of stuff is going to be pretty important. And what you can sort of do, you could make a table like this if you want to. You could even do fourths and fifths, although those get really big really fast, and I'm probably just going to stick mainly to squares and cubes when we have numbers involved. I have a 7th root down here, but don't let that freak you out. We'll see, it's not really that bad. So to simplify these radicals, what am I going to do? Well, I'm going to look at this problem and I'm going to say, okay, this square root of 45, I'm going to look for a perfect square that goes into 45. So perfect squares are in this list. 49 is too big, 36 doesn't divide into 45, 25 doesn't divide into 45. You could use a calculator, right? 45 divided by 25, you get a decimal. 45 divided by 16, you get a decimal. 45 divided by 9, that works. 9 goes into 45. It goes in there 5 times. So I would rewrite it as square root of 9 times 5 in theory. And then I would break that into square root of 9 times square root of 5. Usually, since that always is going to happen, I sort of think of this first step as being optional. You don't really have to write that. You can just skip right down to that next step. Just split it into 2 square roots. And so when I do that, then the square root of 9 is just 3. So I would get 3 times the square root of 5, and that would be my simplified answer. Okay, sometimes when I write this then, when I look at this next one, the square root of 98, I think of it as 2 square roots. And I say, okay, I'm going to have any perfect squares in this first square root. And then I think of the second square root as the leftovers. The 2 insides, whatever I have here and here, they have to multiply to equal 98. And I want this to be the biggest perfect square I can find. And then whatever's left over goes here. So what can I divide 98 by? Not by 81, not by 64. But 49. And again, you can use your calculator. 49 times 2 is 98. So I can rewrite this as 49 times 2, but then the square root of 49 is just 7. So I get 7 times the square root of 2. In this next problem, don't let this 3 on the outside freak you out at all. That 3 is just going to sort of hang out for a while in the problem. I sometimes say it just goes along for the ride. Okay, I'm going to have to try to deal with the square root of 56. And then figure out what that is, and I'll deal with the 3 at the end of the problem. So we can think of this as maybe 3 times the square root times the square root. And again, these are my squares. These are my leftovers. Okay, so I need to find something that will go into 56 that's a perfect square. So something on this list that goes into 56. Well, let's see, 49, that doesn't divide into 56. Neither does 36. 25 times 2 is 50, so it doesn't go into 56. 16, 16 times 4 is 64. 16 times 3 is 48. I don't get 56. 9 doesn't go into 56. 4 does. Now, if you don't recognize that, remember you can use your calculator. 56 divided by 4, if you do that on your calculator, you get 14. So that means I can do 4 here and 14 here. The square root of 4 is 2. So there's really a multiplication there. And then 3 times 2 is just 6. So I would just get 6 times the square root of 14. For the square root of 48, 48, you may not recognize immediately what the largest square root is. You might look at this and just immediately recognize that 4 goes into 48 and that 4 is a perfect square. And that's certainly okay. I can do that. Right, I'm going to have my squares and my leftovers. So I can say 4 goes into 48, 4 times 12. The problem is that square root of 12 is not fully simplified. We said it was simplified if my radical didn't contain any perfect powers of the index. So this is a square root. Is there a perfect square that goes into 12? Well, yeah, 4 goes into 12 again. So I could rewrite this as square root of 4 times square root of 3. And so that would end up being 4 times the square root of 3. Now I could have gotten there faster if I would have recognized at the beginning that 16 goes into 48. So I could have just said the square root of 16 times the square root of 3. The square root of 16 is 4, so again I get 4 times the square root of 3. One note here, sometimes people get square root happy. You don't know when to stop. I've got here the square root of 16 and I write 4. Notice I didn't put another square root symbol. I don't say square root of 4 is 2. We only take the square root once. Once I take the square root, it did its job and it goes away. So the square root of 16, it's fine to say 4, but don't do another square root here. You've got to stop. Obviously, this second way is the more efficient way of solving the problem, but this first way works as well. Let's do a cube root here. So cube root of 54. Remember now, if I'm going to write this out, I'm going to do 2 cube roots. This first one will have to have my perfect cubes, and this last one will have any leftovers. So in this list now, I'm looking for numbers in this column, the last column, that will divide into 54. 64 is too big. It turns out 27 goes in, right? 27 times 2 is 54. You can use your calculator. 54 divided by 27 is 2. The cube root of 27, well, 27 is 3 times 3 times 3. So this is going to just be 3 times the cube root of 2. Alrighty, so now here I've got 12 as a square root of 12, but I also have some variable stuff. We're going to do the same kind of thing. We're going to break it into 2 square roots. One is going to include my perfect squares. The other is going to be any leftovers that I have. So, how about 12? Are there any perfect squares that go into 12? Perfect squares are in this list. Of course, we see 4. So 4 is a perfect square. 4 times what is 12? Well, that would be 4 times 3. So my 4 is a perfect square, 3 is a leftover. For my variables, remember there's really a little index here of 2. We're talking about square roots. So that means I need to be able to divide my exponents by 2 to be a perfect square. Can I divide 4 by 2? Yes. So a to the 4th is a perfect square. All right. Can I divide 16 by 2? Yes. So b to the 16th is a perfect square. Notice I don't have any leftovers from those. That takes up all the a's and all the b's. Finally, is c to the 25th here can I divide 25 by 2? No. So what I look for is what's the next smallest number less than 25 that can be divided by 2? Well, 25 can't be divided by 2, but 24 can. So I'll put 24 C's in my perfect square location. How many C's then are left over? Well, I started with 25. I've accounted for 24. That means I have 1 missing. So that would be in my leftover bin. When I take the square root here, I'm going to get square root of 4 is 2. That's because 2 times 2 is 4. With the a to the 4th, remember I'm dividing the exponent by 2. So 4 divided by 2 is 2. So I get 2 for both of these results, but I get 2 for different reasons. Here I'm thinking what squared is 4? What times itself is 4? And that's 2. Here I say I'm going to take 4 and divide by the index of 2. 4 divided by 2 is 2. So I get the same answer for different reasons. I hope you see that. I also then divide these other exponents by 2. So 16 divided by 2 is 8. 24 divided by 2 is 12. And I still get this bit left over, and that would be my simplified answer. Really, the goal in simplifying a root like this, a radical, is to get what's left on the inside as small as possible. I want this radicand, that's the inside of a radical, I want that to be as small as possible. All right, a couple more examples here. This is a cube root, right? So I'm going to need cubes and leftovers. All right, so 48, is that a perfect cube? No, that's not on this list. I need to find something that divides into 48. Looks like 8 will work. So 8 is a perfect cube. 8 times what is 48? Well, it would have to be 6. 8 times 6. For my variables, I'm going to have to be able to divide the exponent by this index of 3. Can I divide 5 by 3? Not evenly. What's the next number smaller than 5 that can be divided by 3? Multiple of 3 less than 5. Well, I think that would be x to the third, but that's 3 x's out of 5, so I have 2 left over. How about y to the 24th? Can I divide 24 by 3? Yes, so all of y to the 24th is a perfect cube. All right, so there are no leftovers there. The cube root of 8, I say what times what times what equals 8, right? So that would be 2. And then for the variables, I divide those exponents by 3. So 3 divided by 3 and 24 divided by 3. So that would be x to the first. I don't have to write the 1 down. 24 divided by 3 is 8. And my leftovers hang out and stick around to be part of my answer. And one more example here. This is a 7th root. Now I didn't put any numbers. 7th powers get really big really fast. But I have variables here. So I don't have to worry about what to the 7th power, but I'm going to have to try to divide my exponents by 7. So I'm going to get perfect sevenths and then my leftovers. So, what can I divide by 7? Can I divide 14 by 7? Yes. So all of a to the 14th is a perfect 7th, and I have nothing left over from the a's. Can I divide 30 by 7? Well, no. What's the next number less than 30 that I can divide by 7? I think 28, right? I can divide 28 by 7. So that would be b to the 28th. That's 28 out of 30, so that means I have 2 left over. And then finally, can I divide 71 by 70? Well, no. But what's the next number less than 71? 70. That can be divided by 7. I have 70 c's. I started with 71, so I'm missing 1 c. So now I just divide these exponents by 7. So I get a to the 2nd, b to the 4th, c to the 10th, and my leftovers, I have the 7th root of b squared times c.